So again, we are doing some very simple examples of the things we have been doing in class. In the last tutorial, we did examples of all of those were square systems. So I think it's okay that if we repeat the same Gauss-Jordan process, but this time for non-square systems, just to have a feel for them. So let me write some equations. So the first one is wait. Yeah, x1 plus x2 plus 3x3 plus plus x4 is equal to 3. Is equal to 3. Wait, I made a little mistake. Let me put a 3 here. And the next equation in this system is 2x1 minus 2x2 plus x3 plus 2x4. 2x1 minus 2x2 plus x3 plus 2x4 is equal to 8. And it has 4 variables, but only 3 equations. 3x1 plus x2 x2 plus 2x3 minus x4 2x3 minus x4 is equal to minus 1. So again, we can write the matrix first. 1, 3, 1, 1, and a 3 here. You have a 2, minus 2, 1, 2, 8, and then 3, 1, 2, minus 1, and a minus 1. Now, this is our pivot. So, pivot, you have to start from the first line. The first entry has to be pivot. If it's a 0, you exchange zeros. Here it's not 0, so we just make everything below it 0. So minus 2 times this line added to the next row, and minus 3 times this line added to the last row. Nothing happens to this row. And when I add it to the next one, minus 2 plus 2, 0. Minus 6 minus 2 is minus 8. Minus 2 plus 1 is minus 1. minus 2 plus 2 is a 0, minus 6 plus 8 is a 2. And then a 0 here. This time I'm multiplying with the minus 3. So minus 9 plus 1 gives me an 8. Minus 3 plus 2 gives me a minus 1. And a minus 3 minus 1 gives me a minus 4. And a minus 9 and a minus 1 gives me a minus 10. Now, since I'm trying to this time doing Gauss Jordan, so bringing it to the echelon form and then the reduced echelon form. So let's make this one first. Each of our lead non-zero in each row should be 1. So divide by minus 8 gives me a 1. And I'm dividing by minus 8, so gives me a 1 by 8, 0, minus 1 by 4. Still have an 8 here, minus 1, minus 4. Well, what I could have done, I could have added this line to this. But since I have already multiplied that by minus 8, that's okay. I can do it in the next step. First, making this one. All what matters is that the final form has to be echelon. So 1 minus 1 by 8 and minus 1 by 2 and minus 5 by 4. This I got by multiplying this by 1 over 8. Now I can go. I could have added this line to this first and then divided, but I just went the other way. Now I just multiply this line by minus 1 and add it to this. Yes, Akram, Avim, you have a question?
Sir, wouldn't it be like minus 8 in the last row, second entry?
Over here?
You multiply 3 by minus 3, right? And adding 1 to it.
Which step? This over here?
Last row, second entry.
This one? Last row, second entry. This one.
8-1.
8-1.
Wouldn't it be minus 8?
Minus, so I multiplied 3 by minus 3. I got a minus 9. Oh yeah, this has to be minus. Yeah, why did we miss this minus? Is this entry right? Minus 6 minus, yeah, this is right. So this is a minus 1. So that means all I have to do is add these. So when I add these, so I'm adding these two rows. Add a 0, 0, minus half. And when I add 5 1/4 and 1 1/4, I get 6 1/4, which is 3 over 2. Now I can multiply this by minus 2. One, 3, 1, 1, 3, 0, 1, 1 by 8, 0, minus 1 by 4, 0, 0, 0, 1, and over here I got a 3. So I'm trying to bring it into Gauss-Jordan form. That means each of the lead variable in its column, they should be all zeros. So I can take this, multiply it by -3 and add above. So this row is not going to change. Similarly, last row, I didn't touch it. Up there, I get a 0 minus 3 by 8 plus 1. What's that's going to give me? So that gives me minus 3 plus 8, 5 by 8. And nothing happens here. And I have minus into minus 3 by 4 plus 3. $12. So 15. Yeah.
Wouldn't the first row, fourth entry be 1?
First row, fourth entry. Yeah, this is 1. So this is 15 by 4. And now what I need to do is, so this row is done. This row is in the correct form. Now I have to take this and add above with a minus. So this row, because it had a 0 above, didn't need to do anything to this. The second row. And these guys, they don't change. Only this becomes 0 and minus 3, 15 by 4 minus 3 gives me 15 minus 12, 3 by 4. So then I see that x3 is free variable. And I can directly write the solution. X4 is 3, X2 is minus 1 by 4 minus 1 over 8 beta, and X1 is where I'm calling X3 as beta, because I'm going to give it all values. And X1 is 3 by 4 plus 5 by 8 beta, not plus, minus. So from the Gauss-Jordan form, reading the solution is like trivial. So any question?
Excuse me, sir.
Hmm?
Sir, you use the beta function as random variable, right? Like you
Yeah,
could have
you
used
could leave it
y
like you.
or m or n.
Well, beta is just, I just gave a name just to make it more clear that it's no longer a variable. I can give it any value. So beta is any number.
You could have just like given, for example, x is equal to m, j
Anything
or i, and
m
any.
usually we reserve n, m, etc. for integers. It doesn't have to be integer. It's a real number. You could even leave it as x3. Just bring the x3 on the other side, and that
Okay,
should be fine as well.
okay, thank you.
No, let me write this. This is the number 2. Three. Minus 1, 1, beta. And over here I have all zeros. So now my first question is, even before bringing it to the echelon form, I can answer this question. Is it possible for this system to be inconsistent? So what's the answer?
Yes.
Why?
Sir, if beta is
Depends on the value of beta.
Well, if you recall, for an inconsistent system, the last row must take this form. And over here, this can never happen, because whatever row operations I do, I multiply any row with anything, add to any other row. On this side, they're all 0. They don't change each other with any row operation. So this 0 remains 0. So I will never have this form, because I will never have a 1 over here. I will always end up with a 0 here. So always consistent. And this is just what we discussed in the lecture, that such a system where you just give it a special name, where you have all zeros here. This is called homogeneous. So it's a homogeneous system. The next question is, for what values of beta you have infinite number of solutions. So to do that, now you have to bring it to echelon form. Wait, just I'm getting another call, so let me just tell them I can meet them. Yeah, someone, okay, sorry about that. So for what values of beta you have infinite number of solutions. So now let's just try to solve it. And it would be a little bit easier because these things we don't even have to compute. So -2 and just simple add. One, two, 1, 0, -2 plus 2, 0, -4 plus 5, 1, -2 plus 3, 1, and this is 0. This is 0. 2 plus 1 is a 3. This is 1 plus beta, 0. Now I do -3. So this gives me 1, 2, 1, 0, 0. So now I have a -3 plus 1. So that gives me a -2 plus beta and a 0. Now I know that it doesn't matter if it's a homogeneous system. Whenever you have a strictly triangular system, then you're going to have a unique solution. So to not have a unique solution, to have infinite number of solutions, I must have a 0 here. So a 0 here gives me infinite number of solutions. And as a homogeneous system, if it's a unique solution, then that solution has to be 0, 0, 0, all variables 0. And if it's not unique solution, then I'm going to have infinite number of solutions, and so I'm going to have some free variables. So that will happen if beta is equal to 2. For all other values, the solution would be unique, and actually the solution would be 0, 0, 0. No other solution possible. So not many solutions possible here.
Sir, could you show me the blue matrix that you wrote above?
Did I again make a mistake? It's over here.
No, I just wanted to recall something.
So it's here. So we can as well try to find the solution itself. It's just going to take one more step. One, 0, 0, 0, 0. This is the matrix if beta is 2. So now I can use the Gauss-Jordan, make this. So I can see that X3 is free. So I can do -2, 0, 1, 1, 0, 0, this is a 1, 0, -2 plus 1 gives me a -1. So I have X3 is some fixed number, some any arbitrary number, let's call it alpha. X2 is minus alpha, and X1 is alpha. So you can say that it's kind of a, you're finding ratios between these numbers. So the ratios go like this, that X1 is same as X3 and X2 is just minus of those two guys. So anything like that will satisfy. Now let's look at so I'm going to write an equation. X1 plus X2 is equal to 5. And 2x1 plus x2 minus x3 is equal to 6. Well, I don't need to even copy it. I'm not solving anything. And let's say 3x1 minus x2 plus 2x3 is equal to minus 3. Now I want to write it as a matrix equation like we did last time. So that means I think of it as one object, the numbers over here. So I will have this kind of a vector on the right hand side, a column vector. 5, 6, minus 3. And since I have 3 variables over here, I can make a variable vector, a vector of the unknowns, and it also has 3 components because I have 3 variables. Then I will have the matrix of coefficients. 1, 1, 0, 2, 1, 1, 3, minus 1, 2, and this will act on the vector of the variables to give me the vector of constants. So I can write symbolically, give this matrix a name A. A multiplying with the vector X gives me B. So in a sense, when I solve this linear system, solving linear system in this way of thinking is equivalent to solving an equation involving a matrix acting on a vector. So it's just a compact way of writing. So if you see something written like this, a matrix is acting on a vector to give you another vector, you should think of it. This problem may come up from a very different perspective, but you must know immediately that you can think of this problem as solving some linear equations. And if I do the matrix product over here, this matrix acting on a vector, I'll get my equations back. So what was the way of doing the matrix product? A matrix acting on a vector? We had two ways. One was that you think of these row vectors this matrix A is this. Just the row vectors acting on this vector x to give you B, where these row vectors are just the vectors in your matrix. I'm just writing everything explicitly, but you can obviously do it very quickly looking at those numbers directly. So a matrix